In order to graph polynomials from standard form, we need two pieces of information, the degree and the leading coefficient. The degree is the exponent of the highest power of x that appears in the polynomial with a non-zero coefficient, and we denote the degree n, and the leading coefficient is the coefficient of that highest power x, and we denote the leading coefficient a. So for example, in the polynomial f of x equals negative 3x to the fifth plus 2x to the third minus 6x plus 1, the degree is the highest exponent, so 5, and then the leading coefficient is the coefficient of that highest degree term, so that coefficient is negative 3. And we use those two pieces of information to find information about the graph of the polynomial. So the thing that we can tell about the graph of a polynomial based on its degree and its leading coefficient is the behavior at the ends of the polynomial. So what happens on the left side and what happens on the right side of the polynomial. So if the degree is even, that means it's a number like 2, 4, 6, 8, 10, then the end behavior of the graph matches on either side. So whatever happens on the left happens on the right. If the degree is odd, so it's a number like 1, 3, 5, 7, so on, then the end behavior is opposite on each end of the graph. So if the degree is even, two possible things can happen. The ends could both go up, like this, and we don't know quite what happens in the middle. There could be peaks and valleys in the middle, or both ends could go down. So the graph could look like this, and again, we don't know what happens in the middle. We just care that the two ends of the graph match. If the degree is odd, then again, two things could happen. We could have a graph that looks something like this, where the right end goes up and the left end goes down. Or we could have a graph where the right end goes down and the left end goes up. So these are the four possible ways that a polynomial could look, where there could be additional peaks or valleys in the middle somewhere, but we're just thinking about how the degree affects the graph. So with each of these cases, there is a way to determine whether we have both ends up or both ends down, as in these two cases. And that is using A, the leading coefficient. So if the leading coefficient is positive, so the coefficient of the degree term is positive, then the right end of the graph goes up. So in this first graph, where n was even, the right end of the graph is going up. So that means that the A number is positive. So we'll write that A is greater than 0. If the lead coefficient is negative, then the right end of the graph goes down. So in graph number 2, where n is even, you can see that the right end of the graph goes down. So that means that the lead coefficient is negative. In graph number 3, where n was odd, the right end of the graph is going up. So that means that the A value is positive, the lead coefficient is positive. And in graph number 4, where the degree was odd, the right end of the graph is going down. So that means that the A value is less than 0, so the lead coefficient is negative. So these are the four possible ways that a graph of a polynomial could look based on its degree and the sign of its leading coefficient A. For example, let's graph the function f of x equals -3/4 x squared without using a graphing calculator, and only using that information about lead coefficient and degree. So this polynomial has degree 2, and it has lead coefficient of -3/4, which is negative. So what that tells us, since the degree is 2, that means that the ends of the graph match. And since the lead coefficient is negative, the right end goes down. Using that information, we can eliminate some of these possibilities. Possibility A, the ends do not match. That means that that graph has odd degree, so that's not the one that we want. We also know that the right end should go down, since A is less than 0. B and C both have right end down, but D does not. So now how do we decide between B and C? Well, we can plug in a value to the polynomial function to determine which of these graphs is the correct one. So for example, you can see that this point where x is 0 is different on these two graphs. So let's plug in x equals 0 into the polynomial. That would be f of 0, so -3/4 times 0 squared. 0 squared is 0, -3/4 times 0 is 0. So the point x equals 0, y equals 0, or the coordinate point 0, 0 should be on this graph. That means that B is not the correct option, and the correct option is C. So in addition to the end behavior of a graph, we might need to plug in a point or two to determine which graph is correct. So let's do another example with several graphs. We'll match the given polynomial function. So we have 6 possible polynomial functions to the correct graph, using information about end behavior and possibly plugging in points. So this first graph, or this first function, has degree 3, and the a value is the number in front of that degree term. The coefficient is 1, which is positive. So since degree is 3, the ends are opposite, and since a is positive, the right end goes up. So that leaves us with a few possibilities. We could have possibility A, or possibility B, the right end is down, so that's not the correct one. C, the right ends match, or both ends match, but we have odd degree, so that's not the right one. D, the right end is down, so that's not correct. E, the ends match, so that's not correct. We have either A or F. Those are the only two with degree 3 and the right end up. So now the way that we could determine which of these is correct is by comparing a point, and an easy point would be when x is 0 between graph A and graph F. When x is 0, in this function, we would get 0 to the third minus 7 times 0 is 0 minus 10, so we get -10. So f of 0 is -10. That means that graph A does not work. So graph F is the only graph that meets all of those possibilities. Okay. Now looking at the next graph, or the next function, f of x equals -x to the third plus 5x squared plus 2x minus 9. The degree is 3. The lead coefficient is negative. So the two graphs that meet the end behavior requirements are graphs B or graph D. So again, let's plug in x equals 0 to compare these two graphs to decide which one is correct. F of 0 would be -0 to the third plus 5 times 0 squared is 0 plus 2 times 0 is 0 minus 9. So we get -9. Since B has a positive value at x equals 0, the correct option for this graph is D. And we'll just continue to go through eliminating these graphs. Equation 3 has degree 4 and lead coefficient positive. Degree 4 is even, so the ends must match, so that means that we're looking either at graph C or graph E. And again, let's plug in 0 to see which one it is. F of 0 is 0 to the 4th, minus 4 times 0 squared is going to be 0 plus 8. 0 plus 8 is 8, so we are looking between graph C and E for value 8 at x equals 0. So C does not work, it must be E. Equation 4 also has even degree and lead coefficient positive. The only other graph that could have even degree is the one that we just eliminated, graph letter C, so that is the correct graph for equation 4. Okay, continuing on, equation 5, the degree is odd, 5, and the lead coefficient is negative, so we're looking for ends that don't match, right end going down. The only graph remaining that meets those possibilities is graph B, because the right end is down and the ends of the graph do not match. And then finally, equation 6 has degree 5 and lead coefficient positive. So we're looking for ends that are opposite because of the degree, and a right end going up because the lead coefficient is positive, and our final graph A meets those requirements.